we talked about stepwise formation constants, and now I want to talk about trends in stepwise formation constants. So I'm going to give you a very general formula of a nickel aqua case. So if you had nickel hexa aqua, another way to represent this is nickel water and then 7 minus N, where N is 1 in the first case, plus N and H3s. So if it's 1, then this makes sense, and it's easy to understand. But then it could be 2, 3, or 4, or 5, or 6. So this is a general formula for a reaction of nickel with ammonia. And there are some trends in the formation constants here. So Kf is your formation constant. So when N is 1, I'm going to put the log of the formation constant, which is directly related to the formation constant. So the log of the formation constant is 2.72. When N is 2, it's 2.17. When N is 3, it's 1.66. N is 4, it's 1.12. N is 5, it's 0.63. And for 6, it's 0.03. So if you just wanted to find the formation constant, you just take 10 to the power of each one of those numbers. So you can see that as more amines come in, and as you're increasing the order of the formation constant, you're decreasing the actual value of the formation constant. So this is the trend I want you to notice. And this is a trend that you should expect for formation of any metal complex. You will always have K1 greater than K2 greater than K3. If there is not a trend like that, that means there's something changing in the electronic structure. And I'll give you an example. So a change in this trend indicates a major change in the electronic structure, and it's related to ligand field stabilization energy. So I'm going to give you an example here of an iron hexaqua complex reacting with BIPY, bipyridine. You will often see this abbreviated as BPY. If you just take one BIPY and you complex that to the iron hexaqua, you will get 2 waters replaced. So let me draw what that looks like. So a way to abbreviate the whole ligand instead of drawing it is just like that. So you can show that those two are linked. So then if I add another BIPY, you'll get that, and then another BIPY. And the formation of each one of these complexes, and I'm not drawing the complete equation here, obviously, so just abbreviating. This is the K1, this is K2, and this is K3. So these are stepwise formation constants. So you'd expect that K1 is going to be the largest, K2 is the middle, and then K3 would be the smallest number. In this case, the log of K1 is 4.2. Log of K2 is 3.7, and the log of K3 is 9.3. So here we have a trend where K1 is greater than K2, but both of those are less than K3. So you can read this type of trend as a change in the electronic structure. Now, why would the electronic structure have changed? Think about the nature of the ligands. And if we're talking about ligand field stabilization energy, we are talking about maybe how putting Yeah, no, you're right. Go ahead.
It's stronger ligand.
It's a stronger field ligand. So the water is weak field, and the BIPY is a strong field. And BIPY is a strong field. Why? What kind of ligand is it? It's a sigma donor, and it sure is. It's a pi acceptor. So it can accept electrons from the metal into its pi star orbitals. When you have water as a ligand, you will have a high spin complex. So your octahedral splitting will look like this. And, oh, tell me how many electrons are in iron plus 2? How many d electrons? Oops. Yes, there are. So there are 6 electrons in iron 2, and with water as the ligand, it will be high spin. With Bippy as the ligand, you might expect it to be low spin. And that's, in fact, the case. So I'm going to split my orbitals even further and put all 6 of the electrons in the lower energy set. So you've increased that splitting here, so you made this gap bigger when you have Bippy as a ligand, and so all of the electrons will pair before they go into higher energy orbitals, and from that you get increased ligand field stabilization energy. So the ligand field stabilization energy, remember it is 0.4, what is this, T2, G, and EG? So it's 0.4 times the number of electrons in T2G minus 0.6 times the number of electrons in the EG set. And this comes out to a ligand field stabilization energy for water of 0.4 delta O. And for the low spin complex, it's 2.4 delta O. So that's a much larger ligand field stabilization energy. So that iron with 3 Bippy ligands is much more stable than the high spin complex. So you see that there's an electronic structure change that happens between the this complex here and this complex here. And that's represented by that increase in the log K, which is just telling you about the stability of the complex. So that change in electronic structure is very favorable, and it's enough to drive that third equilibrium forward. Okay. There is another effect that contributes to the stability of metal complexes, and it's called the chelate and macrocycle effect. I'm going to compare 2 similar ligands, methylamine and ethylene diamine. So both of these ligands are going to donate to metal ions through their nitrogen. They're both alkylamines, which means they're just a nitrogen attached to an alkyl group. Oops, and I wrote my NH, this should be NH2, of course, not NH3. Okay, so this is a I'm going to call this monodentate. Do you remember what dentate means? A tooth, yeah. Literally means tooth, yeah. It means it just attaches through one atom, where this one is bidentate, which means it can attach through 2 atoms at once, and this is also a chelate. So it's a bidentate chelate. Otherwise, those are the only real differences between the 2 ligands. One's monodentate, the other one's bidentate. Otherwise, they have the same donor atoms, and they should behave similarly. Now, let's look at a reaction where you take nickel bound to methylamine. So we'll have 6 of those. This is a nickel 2 plus complex. And I'm going to add, so this ethylene diamine is also represented as EN. That's the abbreviation. So I'm going to add 3 of those ENs, and I'm going to let a reaction happen. And then I'll get my nickel EN3 complex. That's still an octahedral complex because remember each of the ethylene diamines have 2 donor atoms, still 2 plus. It turns out that this, plus 6 methylamines. The log K here is large. It's 9.3. So that means that the K is 10 to the 9.3. So this reaction is very much favored on this side. And the reason is because of something we call the chelate effect. It's because the thermodynamic stability of a chelate complex is greater than the stability of the comparable monodentate ligands. That's what the chelate effect says. So I'll write that down. But I will just let you know that chelate effect really translates into an entropy effect. The entropy of this system is increased when you bind chelates in replacing monodentate ligands. So the chelate effect is that the thermodynamic stability of a chelate complex is greater than the stability of comparable monodentate ligands. So in the example above, we had two comparable types of ligands. The only difference was one was a monodentate and the other was bidentate or a chelator. Where does this extra stability come from? It comes from entropy. So I want you to reach back into your P-Chem or Gen Chem memories. Remember that there are a couple of equations that tell us something about how the entropy, enthalpy, temperature relate to the equilibrium constant. So I'm going to just relate delta S here to the equilibrium constant K. As delta S increases, or the entropy increases, your equilibrium constant will increase. And that's what we see above in that equation. So I'm going to write two different equations to compare entropies. So if I take a nickel hexamine nickel complex, and I add 6 of the methylamine ligands, how can I tell if my entropy has changed or not? Nope, it didn't. I just forgot to draw it. How can you tell the entropy of either side? Do you remember? Did you ever do this? Yeah, exactly. The number of moles on either side. Or we could just look at it and say number of molecules. So here on this side, how many molecules do we have? 7. What about the other side? Still 7. So we can say that the entropy has not changed during this reaction. And this reaction is pretty close to 50-50 at equilibrium. Now let's look at a different reaction when we're taking the same hexamine nickel complex and reacting it with ethylene diamine. Now what's happened? Yep. Start with 4 molecules. And you end up with 7. What's happened to our entropy? It's increased. So this increase in entropy will increase our stability constant. The K values for these two reactions, let's say that this one's about 1 and this one's about 10 to the 9th. Those values tell you something about the stability of the complex, this complex versus this complex. We can argue it's entropy, that's the energetic reason, but if you think about someone, or a little ligand, grabbing onto a metal with 2 arms, right? If one arm slips off, it's still attached there, and it's a lot easier for the other arm to just come around and wrap. But if you're a monodentate ligand, if you lose hold of your metal, you're floating away. Okay, so it's a lot more stable when there are more than one arms or dentate that are binding to the metal ion. And the more dentates you have, actually, the more you increase the stability. So I'm going to talk right now about a macrocycle effect. If you compare a metal ion that has something like this, just draw. So I'm going to draw a square planar metal complex versus a metal complex that is very similar, yet the ring is closed. This is a macrocycle. A macrocycle is normally more stable than an open chain ligand because the atoms are already pre-organized in a coordination geometry that is going to bind a metal ion. So macrocycles will always be more stable as complexes than an analogous ligand that is not a macrocycle. So this one's more stable. That's what the macrocycle effect is. Some other things to keep in mind. Just like in organic chemistry, when you're making rings out of carbons, 5 and 6 membered rings are most stable. 3 and 4 membered rings form, but they're not as stable. And then 7 and 8 or larger rings will sometimes form, but it's best when you have 5 and 6 membered rings. So 5 and 6 membered chelate rings are most stable. In the example above, I have all 5 membered chelate rings. So I'm going to highlight this in green. So that's a 5 membered chelate ring. You can also have a situation where you have a 6 membered. I mean, you'll see a lot of different situations. And in fact, I think that carboplatin, there's a 4 membered ring. But if you have something like this, that's a 6. And a lot of the times you'll find that there's mixed rings, like in this ligand I'm drawing here. Something where you have a mixture of 5 and 6 membered chelate rings. So you'd have 6 here, 5, and 5. Okay, so we talked about the macrocycle and chelate effect. We talked about trends in thermodynamic stability constants. But in the absence of the chelate effect, what gives rise to stability? So there are a couple things that you need to, actually 3 things that you should consider when you're considering the stability of a metal complex. So in the absence of those 2 things we just talked about. And one of the things is the metal ion itself. So the ionic size to charge, or charge to size ratio, has an effect. So the more highly charged the metal ion is, the more attracted it will be to ligands, which have electron density to donate into that positive center. And the smaller the metal ion is in general, that means that it has a higher charge density, the stronger the complex will be. So there are some trends we can talk about just looking at the periodic table. Let's go first up and down the periodic table for ions of the same charge but of different size. So let's look just at that second column there of the periodic table. Let's start with calcium, strontium, and barium. All of those are +2 ions. So calcium is the smallest, barium is the largest, but the stability goes, so basically stability is going up the periodic table where you have the most stable complexes for calcium for any given ligand set. So you can compare, you can use this to, like if I gave you a calcium hexaaqual complex and asked you to compare it with a barium hexaaqual complex, you would want to use this argument. But you wouldn't be able to use this argument to compare calcium hexaaqua with barium hexamine. Okay, so you would only be able to use this to compare similar ligand sets. So that's one thing to remember. And then going across the periodic table, let's talk about ions of similar size but of different charge. So lithium +1, magnesium +2, and aluminum +3 are all about the same size. But you would increase the stability for a given ligand set as you increase that charge. And then for metal ions that have the same identity except just a different oxidation state, so like iron 2+ compared to iron 3+, the iron 3+ is going to be more stable than iron 2. The second thing you need to consider is related, but it's a little bit different, hard-soft acid-base character of the donor atom or the ligand. Remember, that's your base, and the metal ion or the acid. So based on hard, soft, acid, base character alone, you can predict whether different types of ligand sets will prefer to bind to a given metal ion. And we talked a little bit about that a few weeks ago. And then the last thing that you really need to consider is the ligand field stabilization energy. And this, for this one, we're going to talk about the Irvin-Williams series. And this is really just a series based on observation, but it comes about due to a combination of electrostatics and ligand field stabilization energy. So the series goes like this. Now I'm going to start at barium, and I'm going to go up. I'm only going to be talking about the 2+ metal ions here. So barium is the weakest. Strontium, calcium, magnesium. Now I'm going to go and add manganese to this list. Actually, I'm going to make that one blue because now I'm not going up and down anymore. So manganese, 2+, then iron, cobalt, nickel, copper, and zinc is actually weaker than copper. So this is what we know. So notice that I switched the sign of this guy. This is the Irvin-Williams series. You could memorize it, but there's a lot better way to understand this. So it's based on a combination of electrostatics and ligand field stabilization energy. So if you were talking about ligand field stabilization energy, we need to consider the number of d electrons in all of these metal complexes. So I'm going to make a chart here where this is energy, and along the bottom here I'm going to rewrite that Irvin-Williams series. Yep. What does that do? Wait, zinc is not more stable because of that it's D10. Yes, so the fact that it's D10 makes it less stable than copper because it doesn't have any ligand field stabilization energy.
Oh, right.
So if I just draw a line of what we would expect here based on electrostatics, just on the size to charge ratio of these metal ions, you would expect a direct relationship where the stability of these things would increase as the charge on the nucleus increases or you are closer to the metal nucleus. So barium, strontium, calcium, magnesium, and manganese lie on this line. And I do want to remind you, so let's consider the metal hexaoctal complex. And remember that for all of the first row transition metals, when you have anything weaker field than water, you have high spin. So we're going to consider that these are high spin complexes. If they're not high spin, then you could change this trend. But this is the Irvin-Williams series. It was actually based on a lot of metal water studies, and so it's really valid for high spin complexes. Okay, so tell me about the d electron count of those 5 metal ions that I just placed on that line. Barium, strontium, calcium, and magnesium should be easy. They're D0. So I have a D0, 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 D0. What about manganese 2+? It's D5. So for any of the D0 cases, it is pretty accurate to assume that their stabilities are based only on electrostatics. When you have metal ions that have d electrons, remember that you have an increased stability due to ligand field stabilization energy, except for D5 and D10. So your D5 complex doesn't have any ligand field stabilization energy. So I'm going to just write this down here to remind you. So manganese 2 plus is D5. There's no ligand field stabilization energy there. For iron, what's my d electron count? It is D6. Actually, and I wrote that online, but it's just above that line. What's cobalt? It's D7. And I have even more increased stability. So I'm increasing the distance from this line now. For my D8 nickel complex, I go even further away from the line. For my D9 copper complex, I reach a maximum. I am at the highest difference between this predicted line based on electrostatics and my actual stability. And then for zinc, I go right back to the line. I'm actually right on there. So let's calculate the ligand field stabilization energies for these different situations. Go ahead and do that. Write out the electron configurations for all of these d electron situations and calculate the ligand field stabilization energy. And I want you to explain to me why copper 2 plus is so much more stable than the rest. What? You don't get copper? Yeah. What's ligand? So do you have the ligand field stabilization energies calculated?
Not copper.
What is iron 2?
Iron 2.
Yep. I think 0.8. And then, yeah. And then 0.6, right? So copper has less ligand field stabilization energy than nickel, and yet it's got a bigger gap here between the predicted energy and the actual energy. What might we use to explain that? What do we know about copper? Remember Jan Teller? Jan Teller theorem? Jan Teller says that if there are two sets of, they're orbitals that are degenerate, that are not degenerate in their electron configuration. So this is an example. Here you have, I'm going to circle it in green, you have two degenerate orbitals that do not have the same electron configuration. Jan Teller says that those will split, and you'll have a distortion in the geometry. And it turns out that that's what happens for copper. You could also expect it for cobalt, for iron, but for copper it really matters. So these ligand or these orbitals split to give you lower energy orbitals that apparently give us a much more stable complex. Jan Teller. So this gives us extra ligand field stabilization energy. You don't need to calculate it. You just need to recognize that Jan Teller is responsible for this. Okay, so this difference here is from ligand field stabilization energy, but the extra difference between like a D8 and a D9, you wouldn't be able to predict why there's such a big difference there if you were looking at an octahedral complex. So you have to understand that the D9 complex will undergo Jan Teller distortion, and it makes the ligands around the square plane much more stable than the ligands on the axes, but it contributes to an overall more stable complex. Any questions? Okay, so remember that Jan Teller theorem. It's a big theme, especially for D9 complexes like copper 2.